Welcome to Lecture 9 on our second semester class on stochastic processes. The topic of today's lecture will be the concept of invariant measures for diffusion processes, or for Markov processes in general. We will introduce this notion and we will derive a basic existence result for invariant measures on general Markov processes, for which we will give an example towards the end of this lecture. The concept of invariant measures has already appeared in the context of Markov chains on discrete state spaces, and we want to extend some of the concepts that we have investigated in that segment to the case of general Markov processes on general state spaces. And for that purpose we need a little bit of notation, which we shall introduce as we go along. We start with basically some notation. Namely, suppose we have a measurable space, so just a certain set together with a sigma field curly E, which is defined as a subset of the power set of this set. Then we shall denote with the curly M of E just the set of all measures on this space, which might be in general even signed measures, or measures which do not necessarily give non-negative numbers to sets. And we say we will single out the subset of probability measures, which is then this collection of elements from measure space who are non-negative and who assign a total mass of 1 to the full set. We shall also introduce the concept of the action, or to be precise, the adjoint action of a Markov kernel on measures, which basically corresponds to the consideration of the adjoint of the stochastic matrix, which we already discussed in the context of Markov chains. So the analog of a stochastic matrix in continuous space or an arbitrary space is this concept of a Markov kernel, which we had already developed. And suppose now that we have such a Markov kernel on a general measurable space, then we can talk about the adjoint action of this kernel, which we sometimes denote with a K star. And even sometimes we shall basically omit the star in our notation, but whenever we want to be really precise, we shall make a distinction between the operation of the kernel on functions and the operation of the kernel on measures. So the adjoint operation on measures is basically the dual operation of the operation of the kernel on measures, and we can also define it as follows. So the K star operator converts a measure on my measurable space into another measure, and this operation is given as follows. So the K star operation acting on a measure mu gives a measure which assigns to a set A now the new measure, which is the mixing, if you like, of the kernel measure on the set A, but now averaged out with respect to the argument measure which is subjected to this operation of K star. So in other words, K star mu of A is the integral with respect to that mu of the kernel measure of the set A with regards to that initial position or the starting point. That's the dual operation of the kernel, which is now an operation not on functions but on measures. And in terms of duality, you could also have introduced the following alternative definition, which says that the adjoint action is given as follows. So if you want to integrate the adjoint acting, or the output of the adjoint operation on a measure against an arbitrary Borel measurable function, this could also be defined by writing it as a mu integrated against the K operation acting on the function f. So it's a one-line argument to convince yourself that these two definitions are just the same, where I should probably say that this bracket here that we use here on both sides of the equation is the bracket of the duality pairing between functions and measures, or measurable functions and measures. So this is to be understood as the integral of that function integrated against this measure. Okay, so in this way we have an operation of a kernel on measures, and now comes the actual core definition of today, which is now easy to understand. So if PT now is a transition semigroup on our fairly general state space, then we can consider a measure mu from the state of signed measures, if you like, then we call such a measure invariant with respect to that transition semigroup if that measure is a fixed point for this operation of the adjoint of all these kernels for any time t. So if pt star of mu is the same as mu, in other words, this measure mu, which we want to call invariant, if that measure is a fixed point for this adjoint operation for all these kernels which belong to this transition semigroup. If that's the case, then we call this measure invariant. If, moreover, this measure is not an arbitrary measure, but it is even a probability measure, then we call this measure not only an invariant measure for pt, but we call it an invariant distribution. And we want to consider today the question whether certain invariant distributions for Markov processes exist. And of course, that is a question basically about the long-term behavior of these Markov processes. But before we investigate criteria which would guarantee the existence of such invariant distributions, basically, we shall discuss two simple examples. Namely, for instance, we can consider the Fellers semigroup, which is corresponding to the Brownian motion on, say, one-dimensional space, or just the standard Brownian semigroup. And then I claim that, according to this definition, the plane Lebesgue measure is an invariant measure for this semigroup. As we have stated just before, saying that a measure is invariant for the semigroup is just as good as formulating this invariance in terms of the duality by saying that the pt star operation acting on mu integrated against a function f is just as good as if we integrate the function f against the unperturbed or unchanged measure mu. This is just the same as saying that the pt star operation leaves the mu measure invariant. Now, if we consider this equality, which we would have to prove in the case of the Brownian motion, and if we consider the left-hand side by duality, the left-hand side is just as good as if we integrate the measure mu against, or if we integrate the ptf function, so the initial function after being transformed through the semigroup pt, and integrated that against the measure mu. Now let us write that out just as an integral, as it is ought to be by the definition of this brackets that we use. Well, okay, that's just the left-hand side of this equality which we want to prove. And now we will actually introduce our explicit knowledge of the Brownian semigroup. We know that this operation, or the PTF operation, is just taking the expectation of the f function perturbed by a standard normal Gaussian random variable with proper scaling. So in other words, this PTF operation acting on the function f can also be written as the function f evaluated at the location x plus square root of t times xi, where xi is a standard normal, and taking the expectation with respect to xi, where xi is, let me say it again, a standard normal random variable. Okay, so that here, this formula here is effectively a product integration, or an integration on product space with regards to the distribution of this xi random variable and with regards to the Lebesgue measure. And by Fubini's theorem, we can interchange these two integrations, which then puts this dx integration, so the integration with respect to Lebesgue measure, inside the expected value. And what do I have here? Well, here I have an integral of this shifted function for a fixed realization of xi against the Lebesgue measure, but by shift invariance of the Lebesgue measure for any realization of this square root t xi number. That integration is the same as if I just omit this shift, or if I just put the shift inside this inside this integral, or in other words, the shift invariance of Lebesgue measure tells me that this integral is just the same as if I do not write the shift at all. But now, of course, I see that this quantity inside the expectation with regards to psi does not depend on psi at all. So therefore, this is just the expected value of a constant, which is, of course, just the constant. And that, of course, I can write again as the, if you like, in this abstract notation, this integral is just written as the bracket of the f function against the mu measure, where here mu was supposed to be the Lebesgue measure. So in the end, I have seen that this left-hand side that I started with is exactly the right-hand side of my claim, which establishes the equality, and hence I have convinced myself that, in fact, Lebesgue measure is the invariant measure for plane Brownian motion. Of course, the computation is just the same if we do it in d-dimensional space. And as a remark, of course, we know, or just a remark, that mu, of course, is an invariant measure, but of course it's not an invariant distribution, because the Lebesgue measure on Euclidean space is not a probability measure. It is not normalizable. There is no, it's a measure of infinite mass. As another example, which I just leave as an exercise, we can consider the Ornstein-Uhlenbeck process in the simplest case, which is given as the solution to this simple linear stochastic differential equation. We can use, if you like, the explicit representation for the Mela formula that we discussed in the exercise, for instance, and do a similar computation in order to convince ourselves that this Gaussian measure, in fact, mu, which is the weighted Lebesgue measure with the Gaussian factor in front as a weighting factor, normalized with the proper scaling in front for that to be a probability measure, that this is, in fact, now an invariant distribution for the Ornstein-Uhlenbeck process. First indication why also here this invariant measure is significant also from a statistical point of view. We have the following simple proposition, which again I leave, whose proof I leave as an exercise, which goes as follows. So if we have a Markov process on a general state space and whose initial measure or initial distribution is denoted by mu, and suppose that Pt is the associated transition function for this Markov process, then we can say that mu is invariant with respect to that transition function. Yes, it's invariant with respect to the transition function in the sense of the definition above, if and only if the process xt is stationary, which means that the law of the process, so the distribution of the process at any time, is just constant over time, which means that the marginal distribution of the process does not change over time and is of course mu. This is just a straightforward consequence of the definition of mu being invariant under the action of this semigroup, and it's a straightforward consequence, if you like, of this duality representation of the invariance. I'll leave it as an exercise, and of course this property also gives rise to the name of calling an invariant distribution a stationary measure, because this is a first concept of stationarity of a stochastic process. We call a stochastic process stationary. That's actually the definition. We call it stationary if the marginal distribution evaluated at a fixed time is actually independent of the time at which we do this evaluation. So a stochastic process is stationary if its law does not change over time. And saying that as a Markov process has an invariant distribution is equivalent to saying that the measure is invariant, that the corresponding measure is invariant under the action of the associated transition function. So, even without raising the question of long-term behavior, stationarity is probably something that you would like to see for certain cases of stochastic processes. And only from that point of view, it is an interesting question to ask what are conditions for existence and possibly even uniqueness of such stationary measures. And that's So the first few answers to this question shall be given in this lecture today. We will only make very brief and very rough statements in today's lecture. I will not present all details. I just would like to give a rough sketch of some of the most important arguments here and leave all other details, which you can find many in the literature out there, to your own study, in case you would ever run into such a problem. Okay, so we will now deal with the question of criteria which guarantee the existence of invariant distributions for Markov processes or for Feller semigroups. And our fundamental existence result that we shall present until at the end of today's lecture will be semi-constructive. It will basically provide a constructive approach to producing invariant measures or invariant distributions, but it will also rest upon certain topological or convergence concepts which involve convergence of measures. And of course, one of our favorite concepts for the convergence, or for the notion of convergence of measures, is the notion of weak convergence, which we also know from the central limit theorem, which is one of the most important theorems in probability theory at all. So let me recall to you this notion of weak convergence of probability measures. So for that purpose, we will need to work not with arbitrary measurable spaces, but with topological spaces. And before we consider measures on topological spaces, we start with considering functions on topological spaces. Namely, given a topological space, we can consider this set CB of E, where E is our topological space, which is the set of functions which are bounded and continuous. So it's a larger set than the set of functions which vanish at infinity. The functions which vanish at infinity and continuous are the subset of this CB set. But if we equip this set of functions which are bounded and are continuous again with the supremum or uniform norm, then this is again a Banach space. And the dual space of this Banach space is the set of finite measures. Now, as usual, we shall equip such a topological space unless we have reasons not to do so. We will equip this topological space with the typical Borel sigma field. So it's just the sigma field which is induced from the collection of open sets. And then we say that a sequence of measures on this space is converging weakly to another measure in this measure space, in this space of measures. So the notation or the standard notation for such convergence is this arrow, this half arrow. So we say that a sequence of measures converges to a target measure in the weak topology if and only if, for all functions from this Banach space of bounded continuous functions, the corresponding sequences of integrals converge. That's our notion of weak convergence. And we will use this weak convergence for basically providing constructive arguments for the existence of invariant measures for Feller semigroups. The easiest case, when we basically can obtain invariant measures or invariant distributions at zero cost, is the case when the state space of our Markov process is actually compact. And the reason for this is the following simple but fundamental observation, which says that if I have a compact topological space, then any sequence of the set of probability measures on this compact subspace is precompact with respect to the weak topology, which means that for any sequence of probability measures on this compact space, there exists some subsequence and some probability measure on that compact subset, such that we have in fact weak convergence of this subsequence against that measure. So in one word or in one sentence, it just says that every subset of probability measures on a compact space is pre-compact with respect to the topology of weak convergence of probability measures. This fact is so important that I'd like to sketch it, and I'd like to sketch the proof. You might have seen that already somewhere else, but let me just indicate the proof for you. The basic reason why it's true is that we can take advantage of this Weierstrass approximation theorem. Well, okay, of course I have to be careful. This statement is correct only if this compact space is also separable. That's of course very important. Okay, namely, in the case when I do have a separable compact space, then I can use an abstract version of the Weierstrass approximation theorem to convince myself that this collection of bounded continuous functions, which in this case is the same as just the continuous functions on E, that this is in fact a separable space with respect to the uniform topology. That's more or less a consequence of, in an abstract, it's actually the Stone-Weierstrass theorem that I have to invoke at this case, which is an abstract version of the Weierstrass theorem. So the Weierstrass approximation theorem tells me that polynomials are dense with respect to the uniform topology on a compact subset, and an abstraction of this argument is the corresponding Stone-Weierstrass theorem, which is correct on any compact separable space. So in particular, it just says that I have a countable collection of continuous functions which approximate any given continuous function to an arbitrary precision with respect to the uniform topology. Now, this separability of this bounded continuous function set allows me, of course, to use some diagonal argument as follows. Namely, for every index L for this countable collection of dense functions, I can consider the corresponding sequence of evaluations of integrals of the fixed FL function against this range of mu n measures in my set. Now, since FL is a fixed function and mu n is a subset of probability measures, this is a bounded sequence of real numbers, so therefore it has a convergent subsequence. And then I can do this iteratively for an increasing or ever-increasing sequence, or just for all, subsequently for all indices L, and by employing just the conventional diagonal argument, I can subtract or extract the subsequence eta k such that for all L, for all fixed indices L, this corresponding collection of measures mu n k integrated against the FL measure converges to some number which is denoted by capital L of FL. Now it's straightforward to convince yourself that this L number depends on FL in a linear fashion, so therefore it's even a bounded linear functional, which is easy to show, and therefore by duality, if you like, this bounded linear functional is represented by a measure. This is a consequence of the Riese representation theorem. And hence, by density of this collection of functions FL, I can easily convince myself that I do have actually weak convergence, so that this kind of convergence is correct for any given function, just by approximating any given function by basically a properly chosen linear combination of these FLs. So, therefore, I already have this kind of weak convergence, and the only thing that, if you like, remains to be proven is that this measure mu is in fact a probability measure. But this is a straightforward consequence of the fact that the constant 1 function, of course, is also a bounded continuous function, and therefore, by the weak convergence of this subsequence, also the corresponding integrals against the 1 function converge, but each of these integrals against the 1 function is just a constant 1, because all these measures mu are probability measure. So therefore, I do have in fact found a subsequence eta k or in k such that the corresponding subsequence of measures is converging weakly to that measure mu. Okay, so that's very good. That is very helpful because it basically tells us, or will tell us immediately, that for any diffusion or for any Markov process on a compact state space, provided it's separable, we can find an invariant distribution. I shall present this argument below. But we would like to have a little more flexibility than just working on compact state spaces, of course, where the question is essentially trivial. So we want to extend this kind of weak convergence to the situation, or this compactness of weak convergence to the situation when the state space is not compact. And this is where this famous notion of tightness comes into play. Namely, let E be a topological space, as we shall assume for the remainder of this lecture throughout. And as usual, let us assume that the corresponding Borel sigma algebra is the one that we want to consider for making this space E a measurable space. Now, let us take an arbitrary family of probability measures on that space. Then we call this family of probability measures tight. That's the technical term. We call it tight if for any epsilon positive we can find a compact subset of this topological space such that all these measures give almost no mass to sets outside this compact subset, which means that for all elements in my chosen family, the total mass of everything outside this compact subset is no bigger than epsilon. This means, this is the definition of tightness of a family of probability measures, and it means that these measures all have something like an effective support on a joint compact subset. There's a little bit of an error that each of these measures can produce, but this error is outside a joint compact subset. And this error is uniformly controlled uniformly by an error epsilon. Okay, let me say it again. A collection of probability measures on an arbitrary topological space is called tight, or a collection of Borel probability measures on a topological space is called tight if for any error level epsilon I can find at least one compact subset that up to error of epsilon all these measures have their support on that fixed compact subset. In other words, it says that all the music and almost everything that's relevant for all these measures is happening on a joint compact subset. The connection between this tightness concept and the notion of weak convergence of probability measures is given through the so-called Powerhoof theorem, which is a famous and fundamental theorem in probability theory. And it goes like this. So let E, a set, together with a metric, be a Polish space, which means that D is a complete metric and such that E allows a countable dense subset. And let us equip this set E with the corresponding Borel sigma field, which in other words is the sigma field induced from open balls which are defined in terms of this metric D. Then a sequence or a family of probability measures on that measurable set is pre-compact with respect to the weak topology if and only if this set is tight. We will use this Prokhorov theorem only in one direction in order to make sure that we do actually have weak convergence or that we have a pre-compactness. So therefore we will sketch only the proof of this Powerhoof theorem in the direction in which we shall use it. Namely, let us assume that we have a sequence of probability measures on such a Polish space which happens to be tight. And what we want to show is that we can select the subsequence of this sequence of probability measures which converges weakly. So for that purpose, let us fix a sequence of error values epsilon L which converges to 0 and choose a sequence of compact subsets in the set E such that in fact the measures give uniformly almost all mass to the complement KL with error value epsilon L, and without loss of generality we can also assume that the sequence of compact subsets is increasing. Then we can apply the previous compactness argument for the case when the state space is compact, basically to each of these chosen subsets KL for fixed L individually, making sure that we have weakly convergent subsequence on each of these fixed compact subsets. And then by applying a diagonal argument again, we can make sure that we can select the subsequence of our sequence of measures such that this subsequence of measures, when restricted to a fixed compact subset KL, that this sequence of measures converges to a certain measure mu L on this compact subset KL. That's for sure possible because we have this property that probability measures or measures which have a bounded total mass are in fact pre-compact with respect to the topology of reconvergence on any compact subset. That was the previous fundamental assertion based on Weierstrass approximation. And moreover, by the fact that these compact subsets are increasing, and since we choose again and again subsequences, this diagonal argument also entails that the restriction of the measure with index L plus 1, which is a measure on the compact subset KL plus 1 when restricted to the compact KL of one index below, that this limiting measure coincides with the limiting measure of index L. So in that regard, we have a consistent family of measures on this increasing collection of compacts. And for that purpose, we can properly define the following measure on the full set E, which is defined for any Borel subset B, we define as the measure of that Borel subset B, if you like, to be simply the limit of the corresponding measures that we obtain when we intersect this set B with the compact KL and evaluate that measure with respect to the measure of index L and let this quantity tend to infinity, or let this sequence of quantity tend to. So this limit exists by monotonicity, and it's uniquely determined and defined through this consistency property. So therefore, we have defined a measure which is then, of course, a non-negative measure on the set E. And since the total defects which we could have observed on the complements of these mu L's outside of these compact sets, that these total defects is a zero sequence, we can also conclude that the total mass of these newly defined measure on the full set is equal to 1, which after all completes the proof of this assertion. So that's the sketch how the Powerhoof theorem produces or asserts the existence of a weakly convergent subsequence, provided we have this tightness of that family of probability measures. The Prokhorov theorem will be our basic tool, semi-constructive tool, if you like, for the existence of an invariant measure, but now we have to connect this to our theory of semigroups, and for that purpose we have to introduce one more element of notation. This is necessary because we want to connect to our theory of Feller semigroups, and there is a little subtlety here in what we want to do and what we have done so far with regards to Feller semigroups. Recall that up to this moment our concept of Feller semigroup was a theory of semigroups acting on functions which vanish at infinity. And the functions which vanish at infinity, that's in general, of course, a strict subset of all functions which are bounded and continuous on our space E. So somehow we have to make the bridge between this subset of functions to the entire collection of bounded continuous functions. And this is why we introduce the following little bit of terminology again. Namely, if we have a topological space, which as usual is equipped with the Borel sigma field, and if we have a transition function on this topological space, then we call this transition function, so recall that transition function is this family of kernels which satisfy this Chapman-Kolmogorov equations. Then we call this transition function a CB transition function, where CB stands for the collection of continuous functions which are bounded, if the application of this transition kernel as an operator on functions produces again a function which is continuous and bounded, provided the function on which we apply the operator pt is a continuous and bounded function. So we call this transition function, or this family of kernels, we call it a CB transition function if it maps bounded continuous functions into bounded continuous functions. So let me highlight again what is the difference towards what we introduced in the context of Feller semigroup. Well, in the context of Feller group, we were asking for this invariance of this function space only when we restrict the function space to the functions of continuous functions which vanish at infinity. And here we want to have, in a way, a slightly stronger property, namely that not only functions which vanish at infinity are mapped into continuous functions which then also vanish at infinity. Here we want to ask, is it so that a bounded continuous function is mapped onto a bounded continuous function? And finally, we call a conventional Feller semigroup, in the sense as we had discussed so far. So a conventional Feller semigroup, which by definition acts on functions which are continuous and vanish at infinity, we call this Feller semigroup a CB Feller semigroup if the associated transition function is in fact a CB transition function. So in other words, if this Feller property basically extends not only, or can be extended from the functions which vanish at infinity to the functions which are just bounded, and we do not necessarily need to vanish at infinity. So if the space E on which we work happens to be compact, of course, then there is no distinction between these two sets of functions, because the function, the whole set is compact anyway. So therefore the notion of vanishing at infinity is an empty notion. But if the space E on which we work is not compact, then of course the functions which vanish at infinity, this subset is a proper subset of all bounded functions. For instance, the constant function 1 is of course a continuous function which is bounded on the entire space, but it's not a function which vanishes at infinity. So for instance, on the real line, the constant function 1 is a bounded continuous function, but it is not a bounded continuous function which vanishes at infinity. Now, if we have a Feller semigroup which comes along with a transition function, as we know, so we can associate to this Feller semigroup this collection of transition kernels, and if these collection of transition kernels, if we use them to define an operation on continuous bounded functions, if these transition kernels give rise to a self-map on the set of continuous bounded functions, then we call this Feller semigroup a CB Feller semigroup. This raises the question when we can make sure that a Feller semigroup is in fact a CB Feller semigroup, and for that purpose it suffices to check basically that exactly this constant 1 function, if we apply this Feller semigroup to the constant function 1, that this actually is again a bounded continuous function. This is a useful and easily checkable criterion, which is surprisingly something that I found only in the recent literature by René Schilling from Dresden, which is, this statement is, like 15, 20 years old, but it is helpful in order to sort out these different concepts of a Feller semigroup. So the criterion of Schilling is like this. It says that a Feller semigroup, in the conventional sense as we discussed, right from the start of this semester, a Feller semigroup on a Polish space E is in fact also a CB Feller semigroup if and only if the constant function 1 is mapped onto a continuous and bounded function on E. So what you want for a CB Feller semigroup is that this is correct for any F. That's the property that you would want to see. But by Schilling's criterion, it is enough to check that this property is correct when you specify this function f to be exactly just the constant 1 function. If you think about this criterion, it's quite evident, and I leave as an exercise to prove that this statement is actually correct. And as a corollary to this proposition, of course, we know that if our Feller semigroup happens to be conservative, so if Pt of 1 is exactly 1, then this criterion is obviously satisfied. So in particular, all conservative Feller semigroups, all conservative Feller processes are also necessarily CB Feller semigroups. Okay, so if we want to apply now the subsequent existence theorem, which guarantees the existence of an invariant measure, or invariant distribution, in fact, if we want to apply this criterion, we will need to check that our semigroup that we constructed as a Feller semigroup will satisfy this additional CB Feller semigroup property by means of that criterion which we have just stated. And with this notion of a CB Feller semigroup, we can now state one sufficient criterion for the existence of an invariant distribution, which is the so-called Bogoliubov-Krylov criterion. I would emphasize at this point once more that I'm giving only one stream of arguments which leads to the existence of an invariant distribution for a Markov process. There is a huge body of literature out there which deals with more refined and more complicated arguments why certain Markov processes do have invariant distributions. And here in this lecture, I chose to present a streamlined sequence of arguments, which is conceptually easy, but nevertheless quite powerful in practical applications. And this Bogoliubov-Krylov argument is used in many applications. And whenever you want to prove that a certain Markov process admits an invariant distribution, this Bogoliubov-Krylov type of argument would be one of the first things you would always try before you look into the literature for more refined arguments. So here's the statement of that criterion. Namely, let Pt be such a CB Feller semigroup in the sense as we discussed. And suppose that for some position L from some standpoint x in the state space E, you have that the following family of probability measures, or the following family of measures, in fact, is tight. Namely, we construct what is sometimes called the occupation density measure. So recall that PS of x and A for a fixed position x and a subset A is to be interpreted as the probability of the Markov process to be in the subset A of my state space when it starts at position x and when we let s units of time run. So what we do here is we take for a given time t, what we take is the average probability. When we average with respect to the time parameters, we take the average probability of the process to stay in the subset, or to be in the subset A of my state space when I average with respect to the time parameter on the interval from 0 to t. And since I want to take the average of this, of course, I divide this whole thing by 1 over t in order to have a real averaging, like some sort of an arithmetic average. So if, for instance, all these kernels PS are actually Markov kernels and not only sub-Markovian kernels, then this is what we would call a mixing of this family of Markov kernels with respect to the uniform distribution on this time interval from 0 to t. And in particular, this mu t measure here would be, again, a probability measure. If, as we shall typically assume, this Markov process P is only sub-Markovian, then this resulting measure mu t is a sub-probability measure, but at least it is still a measure which has a finite total mass. Okay, so the Bogoliubov-Krylov argument, we consider this family of sub-probability measures or probability measures in the conservative case. And if we assume that this family of sub-probability measures is tight in the sense that we discussed above, then this semigroup, this CD-Feller semigroup, has at least one invariant distribution. That's the Bogoliubov-Krylov criterion. Let me say it again. So suppose you are given a Feller semigroup, which happens to be a CD-Feller semigroup. Then what you do is you consider these occupation density measures, mu t, and if you can assert that this family of occupation density measures is tight, then you can conclude that there exists at least one invariant probability distribution for this family of Markov kernels, or for this Feller semigroup. Before we prove the Krylov-Bogoliubov criterion, let me highlight and stress that, of course, this criterion does not say anything about the uniqueness of the invariant distributions. For that, we would need to have a different type of argument, and it's not the contents of today's lecture to highlight the uniqueness or to deal with the uniqueness question. The Krylov-Bogoliubov argument is only used to prove the existence of some invariant distribution. Okay, let us now prove that, in fact, this tightness of these time average density measures is enough for the existence of an invariant distribution. Namely, by our Prokhorov theorem, we know that we can choose some subsequence of t values which tend to infinity, such that the corresponding occupation density measures converge to some measure which we denote by mu star. And what we want to show is that this mu star is in fact an invariant measure for this semigroup. The invariance of this semigroup means that if we use a dual formulation, that for any bounded measurable function, for any bounded continuous function, that is enough to check that for any bounded continuous function, when we apply the semigroup for a given time value s to that function f, and we take that into the integral with respect to mu star, that in the end this is just as good as if this ps operation hadn't been applied to the function f. So what we want to show is that this quantity here that we start to investigate, that this quantity is just the same as the quantity which is obtained by not transforming the function f with the semigroup p at time s. Okay, so therefore let us write out what this object actually is. Ps f integrated against the mu star. By definition, the mu star is the limit of this average measures, which are basically the semigroup measures for a fixed initial position. But by definition of our dual operation of the induced from this family of Markov kernels, we can write this PS or the PU measure also as the resulting measure which is obtained by hitting the Dirac measure for starting at the initial, it's concentrated on the initial position, and hitting this with the dual operation of the semigroup. And so therefore this integral of the PSF against the PU is nothing but this dual product. Then, if you like, by a Lebesgue-dominated convergence, we can interchange this integration with respect to the time axis with the duality formula such that we have this duality inside the time integral. And finally, by another application of Lebesgue-dominated convergence, we can also take this limiting procedure with respect to the k operation outside of this expression. Now we can map, or we can move this PS operation onto the right-hand side in this duality product. So instead of writing PSF integrated against this measure, we can equally write that this is just the f function integrated against the measure which is obtained by hitting the Dirac measure at position x with the dual semigroup, but now we're using the semigroup property, which of course translates to this corresponding semigroup property for the dual operation, which is now hit by the semigroup at time u plus s. And here, of course, I use the property that also the dual of the semigroup has this semigroup property. Okay, but now I see that I have basically almost the same expression as for the actual measure mu star with a little bit of the perturbation, because now I have this shift in the integration parameter. That, of course, can also be rewritten by doing a global shift of the time domain over which I take this integration. This is done here, so I just do a change of variables, shifting this integration domain over which I do the integration with respect to this time parameter. And then, since all these quantities here are bounded, it's a simple exercise to prove that this limit which I obtain here is just the same as if I do not do this shift here in these axes, because I divide by a growing, ever-growing quantity, which in both cases does not contribute to the limit. So therefore there's perturbation correction. So the fact that I'm dividing by a growing quantity here produces that this additional perturbation, which is obtained by these finite integrals here, will be cancelled in the limit. So therefore this little s perturbation does not contribute, and I can just omit it, and I see that I'm ending up with exactly the expression that I want to see, which brings about again the mu star as the limit of this integration. So you see, it's just a very simple plain argument. And so what did we use? We used the fact, of course, that we can subtract this subsequence, that we can write this tested integral by means of this duality and this time averages, and then we use the semigroup property of the dual semigroup and the fact that these little perturbations, as they turn out, are bounded. So therefore, if we divide by this growing sequence of numbers in the limit, they do not contribute. So we can then ultimately arrive at the one typical practical application or practical criterion which you can actually really use in practice to convince yourself that there is at least one invariant distribution for a Markov process. This is the so-called Yapunov function criterion, which is a very handy criterion and which applies these arguments which we have developed so far in order to come up with a really quick and very useful argument. So the statement goes like this: if we have a Markov process on a Polish space, so for instance, typically a solution of a stochastic differential equation on some Euclidean space or so, and if it is so that this Markov process induces in fact a CB Felassen group, as we said, and let us denote the corresponding generator A with its domain D of A, and assume that we find a function f in the domain of the generator, and suppose we find a function g, which is a continuous function on the state space, which is non-negative and which has compact sublevel sets, which means that for any level L from the non-negative real line, if you look at the pre-image, or if you look at all these arguments, all these states in G, which belong to the set where the function G is below the level L, then we want that for any such threshold value L, this corresponding set, this sub-level set, is a compact set. And suppose that we also have some constant function C, such that if we apply the function, if we apply the generator A to this function f, the resulting function is bounded from above by a constant minus this g function. Then this semigroup or the diffusion process has at least one invariant distribution. So before we prove that and we give an application to a concrete diffusion process, let me illustrate what this actually means. So the typical picture you should have in mind is that if that's your state space and this is your function g, what you would want to see is that the function g grows at infinity so quickly that if you fix a certain level L and you collect all the functions, all the positions x, which are so that's the graph of the function g, are so that this is below the level L. So this would be, if you like, the piece of space which is exactly now this sub-level set. What you want is that this is a compact subset. Well, of course, a constant function g would not have this property, right? So if you choose, for instance, g to be the constant function 1, then for level L equals 2, for instance, the corresponding sub-level set is the entire space, and that is in general not compact. So what you need for the function g, for this to be true, is that the function g grows sufficiently fast. Now, on a locally compact subset, this is equal, or is basically equivalent to saying that the function is diverging at infinity. But if you have non-locally compact subsets or spaces, then you have to enforce stronger conditions for a function g to have these compact sub-level sets. But in many, many cases, or at least when you work on locally compact subsets, basically this compactness of sub-level sets is basically just saying that the function g grows sufficiently fast at infinity. Okay, so that's the picture that you should have in mind when we talk about functions g which have compact sub-level sets. And let me state or rephrase this Lyapunov criterion then once more. So suppose you have a Markov process on a polar space which induces a CB Feller semigroup, and suppose A and D of A are the generator with its domain, and if you are lucky enough to find a function f in the domain of the generator such that the application of the generator to the function f produces a function which is bounded from above by a certain constant minus a function, minus a non-negative function which has compact sublevel sets, then this Markov process or the corresponding semigroup has at least one invariant distribution. That's the Lyapunov function criterion. I should also mention that there are many versions of such Lyapunov function criteria. And here I chose to present, in a way, probably the simplest version of all these huge amount of Lyapunov function criteria. So the idea here is again that this Lyapunov function thing is that you try to make a statement about the process by looking, of course, at the generator, and if the generator is sufficiently contractive, so to say, which you, at least on one function, which you have to particularly find, then you can make a statement about the behavior of the process. We would like to use this Lyapunov function condition on very general Markov processes, which might be induced from solutions to stochastic differential equations or not. And for that purpose, we would like to make now really a probabilistic argument, which involves a Martingale statement. And here we make use of a general so-called Dynkin formula, which is basically a consequence of the Ito formula in case of stochastic differential equations. But for general Markov processes, there is an equivalent statement, which is an extension in a way of a consequence of the Ito formula for general Markov process. And it goes like this. So if you have a Markov process or Feller process, say, on a space E, and if that Markov process, of course, has a generator, or it uses, if you like, a Feller semigroup with a generator A and D of A, then for all functions f in the domain of the generator, the following stochastic process is a martingale. So this is now formulated in the context of Feller semigroups. Namely, you take your Markov process x and you evaluate the Markov process by means of the function f. That's a real valued stochastic process. That, of course, will in general not be a martingale, but it's a semi-martingale. That's part of the statement. And you can convert this, so the compensator of this semi-martingale is the time integral of the application of the operator A to the function f evaluated along the trajectories of the process. And then the corresponding process, which is a process in the time parameter t, this is a martingale. That's the statement of the Dünkin formula. Now, as an example for this, we can come back to the example of Brownian motion. In case of a Brownian motion, we can take any C2 function, if you like, which vanishes at infinity or so, and then this would be the evaluation of the function along the trajectories of Brownian motion. And we already know by an Ito formula that if we subtract the generator applied to that function and integrate that along the trajectories with respect to the time axis, in this case it would be the Laplacian operator, 1/2 the Laplacian, then we obtain a martingale. So let me say it again. So for a function f in one dimension, say, which is sufficiently smooth, if we evaluate Brownian motion, and if we subtract from this the time integral of the Laplacian of the function f, and this would be just second order derivative, Laplacian of f evaluate on the Brownian motion ds, well, then we know that this is a martingale. This is a straightforward consequence of the Ito formula. In the case of a Brownian motion, the corresponding statement is also correct if the process B is not Brownian motion, but the solution to a stochastic differential equation under sufficient regularity conditions on the coefficients. And the corresponding result does even extend to the very abstract situation of a Markov process, which is defined only in terms of its generator. This statement about this martingale property is more or less a straightforward consequence of the Markov property together with the semigroup property and taking differentials, and I leave it as an exercise to you to convince yourself of that the validity of this statement also in this general case of, say, Feller processes. Okay, we can now put all these elements together to actually finally prove our Yapunov criterion. So we take this function f, which we have found, so it's our Yapunov function f, and by this Dünkin formula, we know that if we evaluate the function f, if we evaluate the function f along the trajectories of this Markov process, and we subtract this time integral of the A operation on f along the trajectories, then this gives a martingale. We can, of course, if you want, add or subtract the initial position of this function evaluation on the trajectory. It's just a constant which does not destroy the martingale property at all, but in this way we have a martingale which starts in 0. So therefore, if we work modulo martingales, we have this identity. Now we use the fact that this A operation on the function f is bounded from above by the constant times the g function. So therefore, if we plug this bound into this integral, we obtain this upper bound for this evaluation of this integral. That's an inequality which is correct almost surely. So therefore, if we take the expectation on both sides of this inequality, we see that on the left-hand side we have this, and if mu naught is the initial position or the initial measure of this process, and if as above we take as mu t these occupation density measure, these average measures, Then we get, after taking expectation on the left-hand side, we get the operation of the PT, semi-group of the acting on F, integrated against the measure, the starting measure mu naught, minus simply the measure mu naught or the function F integrated against the measure mu naught. On the right-hand side, we get the minus of this time integral combined with the expectation. But this is nothing but, if we divide by 1 over t the whole both sides, this is nothing but exactly this integral of the g function against this time averaged or occupation density measure. And since this comes with a minus on the right hand side, I can also pull it on the left hand side of my inequality, but now with a plus sign. And on the right hand side, of course, I get the CT. First of all, I get the CT, but this is then, since I divide both sides with by t, this is just on the right hand side, just gives me a C on the right hand side. Okay, now if f is a bounded function in the domain of my generator, these numbers here will be finite all the time. So in particular, if I divide by 1 over t, this will be for t large, this will be just as small as I want. And in particular, I can conclude from this inequality that the collection of all these numbers, which I see here on the left hand side, the collection of all these integrals of this fixed g function against all these various occupation density functions on the occupation density measures, this is a globally bounded quantity. This is what I write here. So the supremum of all these integrals of the g function against these density measures is bounded from above by a certain constant, which is finite. Okay, and that's now where I want to conclude. I use now, if you like, a version of the Chebyshev inequality. I want to convince myself now ultimately that this sequence of occupation density measures, or this family of occupation density measures, is tight. And for that purpose, I evaluate, for a moment, for a given value of L, I evaluate the measure under the measure mu t of the set which is obtained by the superlevel set of the g function at the level L. And then by the usual Chebyshev argument, I can write this measure of this set also as a measure on the full set combined with an indicator. So it's just the integral of the mu measure against the corresponding indicator, and the indicator of this one level of the one constant I can also write as a quotient of L by L. But then, since on this set g is greater or equal to L, I can produce an upper bound on this integral by replacing this constant L with the actual value of the g function, and then ultimately I can pass to the full integral, since g is non-negative, of the g function on the full set, which then produces the integral of the g function against the mu t. And now I use the fact that this quantity here, as I had just convinced myself, this is a bounded quantity. It's bounded by a certain finite number k from above. So this whole expression on the right-hand side is bounded by k over L, which means that if I choose L sufficiently large, this integral is uniformly small, for instance, smaller than a given value of epsilon, if L is chosen sufficiently large. Which in other words means that the corresponding measure mu on the complementary is greater or equal than 1 minus epsilon. So in other words, this means that mu t of the corresponding sublevel set, this is greater or equal to 1 minus epsilon, because it's a complementary set. But this is a compact subset, because we assume that g is a function which has compact sublevel set. So therefore, and since this is uniformly small, or uniformly big, uniformly among all, with regards to all these parameters t, I have in fact established the tightness criterion which is asked for in this Bogoliubuv-Krylov argument. So therefore, in fact, this collection of measures mu t is tight, and I can invoke my Bogoliubov-Krylov criterion to convince myself that, in fact, this semigroup or the corresponding Markov process has an invariant, at least one invariant distribution. I want to give now an example, probably the simplest possible example for a successful application of this Yapunov method in the case of a in case of a Markov process which is induced from a one-dimensional stochastic differential equation. Namely, consider the stochastic differential equation dxt being minus b of xt dt plus dwt, where b is a function which is growing at least linearly at infinity, which we formulate as follows. So bx times x is greater or equal to alpha times x squared minus c for some positive alpha and some constant c, which basically says that at least the function b is behaving basically like a gradient of a quadratic function, at least like a gradient of a quadratic function or higher power, when we consider when outside a compact subset or something like that. We know that these solutions of such a stochastic differential equation give rise to a Markov process. We have discussed the fact that this induces, in fact, a Markov process under probably additional assumptions on the function b. But again, at that segment, we were restricting the situation to a simple case. The fact that these solutions induce a Markov process extends to a much broader class of functions b, and this is the case here as well. So the solutions of this stochastic differential equation induce, in fact, a Markov process, a Feller process, in fact. And we know that the generator on sufficiently smooth functions will have the form which is the consequence of Ito formula. AF is minus BF prime plus 1/2 F double prime. That's the generator of this Markov process. On sufficiently smooth functions, on the Markov process which is induced from solutions to this. And we want to check now that these solutions, or that the corresponding stochastic process does have at least one invariant distribution by using this Yapunov approach. And we take as a Yapunov function f here the square function. Now the evaluation of the generator of this square function produces then a minus, evaluated at position x, evaluates a minus 2 of x, b of x plus 1. That's just a straightforward application of the formula above here to the case when f is the square function. And by the assumption on the growth of the function b at infinity, we can bound this from above by minus 2 alpha x squared plus 1 plus c. And therefore the function g, which is the function which is supposed to have compact sublevel sets, is here this function 2 alpha x squared. So it's exactly the square function, or the parabola, which is our g function. Of course, this is a function which grows at infinity. And since the Euclidean line is, of course, locally compact, we see that this is, in fact, a function which has compact sublevel sets. So, as a matter of fact, we see that any solution to such a SDE for a B satisfying this growth condition produces or will have at least one invariant distribution. So you see that once the Yapunov condition is established, you can work with that quite effectively.